Hello everyone, Kodongane, the native god here. Alright, so let us look at this question. Right, so the question is on motion, power, and energy. Right, we are going to make use of motion graphs, kinematic equations, or equations of motion. Right, so looking at 1.1, define the term mass of an object. Right, now there's probably a number of ways in which you can define the mass of an object. Right, so this is just one of them. Mass of an object refers to the quantity of matter that a body possesses. Right, that is just the easiest way in which you can define the mass of an object or mass. Right. 1.2, distinguish between displacement and distance. Right. The major difference between the two terms is essentially the fact that one is a scalar, the other one is a vector. Right. With distance, we only consider the magnitude of the distance, right, but no direction, making distance the scalar. And then with displacement, right, we consider both magnitude and direction, which makes displacement a vector. Right, so when distinguishing between the two, right, you simply state the fact that displacement is a vector, whereas distance is a scalar quantity. Right, that's the difference between the two, or that is how you distinguish between the two. Right, now let's look at 1.3. 1.3 reads as follows. A Toyota Yaris moves from rest and accelerates for 15 seconds and reaches a velocity of 20 meters per second. It continues with the uniform velocity for 15 seconds and the driver brakes and the car stops after 10 seconds. Right, now we haven't necessarily been given a graph for this problem, but because essentially, if you look at the statement, the car moves in stages, right? There's part of the motion of the car where the car is accelerating. There's part of the motion of the car where the car is moving at uniform velocity, and there's a section of the motion of the car where the car is decelerating, right? In such problems, I always advise students to, even if it is not required, right, but to draw a graph. The graph will give you context as to what exactly is happening in the problem statement. Right, it simplifies a lot of the problem. Right, so the first thing I would do here, or that I would advise you to do, is to, even if you don't draw it on a piece of paper, even if you draw it on the question paper itself, just draw a rough sketch of the velocity time graph, right, so that you have an idea of what exactly is happening. Right, so this is 1.3. right, so instead of writing down what you've been given, because the motion is extensive, meaning that you get different stages or different sections of the object's motion, it is better that you instead quickly draw a rough sketch of the graph. Right, so your graph would look like this one here. Right, as you should know by now, along the y-axis, the velocity time graph along the y-axis has velocity in meters per second, and then along the horizontal plane, it is time in seconds. Right, now the statement said you have a Toyota Yaris which moves from rest is 0. Right, so when they say it's moved from rest, it means it is moving from 0 and it accelerates for 15 seconds, right, and reaches a velocity of 20 meters per second. So we are told that this Toyota Yaris moves from rest, so it moves from 0, it accelerates, right, for 15 seconds. So from 0, it accelerates for 15 seconds. After accelerating, after 15 seconds, it is at a velocity of 20 meters per second. Right, so this is how the graph looks like after 15 seconds. And then they say it continues with a uniform velocity. Uniform means constant, right? So meaning that once the Yaris reaches a speed of, or a velocity of 20 meters per second, it continues with a uniform velocity. So it stays at this velocity, right, for 15 seconds. Hence on the graph here, they said, right, from here it continues at a uniform velocity, right? So hence we have a straight line. The straight line, right, essentially means that the velocity here is constant, right? They said it continues at a uniform velocity for 15 seconds, right? So from here, for 15 seconds, the velocity is uniform, right? Now remember that from rest to 20 meters per second, right, the time was 15 seconds, and then it continues moving at a uniform velocity for another 15 seconds. That is why here you have 30 seconds. So the 15 plus the 15 seconds that it moves uniformly, right, gives us 30 seconds. Right, so after 30 seconds, the graph looks like this here, right? And then they say, and the driver brakes and the car stops after 10 seconds, right? So from this point, right, the car starts braking and it decelerates, right? And then after 10 seconds, it comes to a complete stop, right? Hence, you see after 10 seconds, right, the velocity of the car is essentially equal to 0 meters per second. Right, now they said that this section, so the deceleration takes 10 seconds. At this point, remember, it was after 30 seconds. So 30 plus the 10 seconds it takes to brake from here to there. Right, you add that up and you get 40 seconds. Right, and your final velocity time graph should look like this one. All right, now let's look at questions. 1.3.1 calculates the acceleration in the first 15 seconds. All right, 1.3.1 calculates the acceleration in the first 15 seconds. In the first 15 seconds, this is what they are referring to. Right, they want us to calculate this acceleration here. All right, now what is the acceleration there? Remember, one of our equations of motion is v is equal to u plus at, right? If you solve for acceleration here, or if you make acceleration the subject of the formula, take that side, you're left with at is equal to v minus u, and then of course you get rid of t by dividing both sides by t. So essentially meaning that acceleration is equal to v minus u divided by t, right? So we get this equation from the equations of motion, right? Right, so acceleration is equal to the final velocity minus the initial velocity divided by t in the first 15 seconds. So in this section of the graph, right, which is the first 15 seconds, right, the initial velocity is 0. The final velocity in this section is 20 meters per second. And what is the time? The time it took to move from 0 to 20 meters per second is 15 seconds. So now you substitute, right, the final velocity in the first 15 seconds is 20. So you have 20 minus the initial velocity, which was 0, divided by the time it took to move from 0 to 15 seconds, which is 15 seconds. Now if you punch this in your calculators, you are going to get 1,3 recurring. Now always round off your answers to 3 decimal places. So 1,3 recurring, you are going to write 1,333. Acceleration, the units of measurement of acceleration is meters per second squared. Right? Now let's look at 1.3.2. Right, calculate the total distance of the entire motion. Right, now remember that here you weren't required to draw the graph, right? So the quantities we are determining, we are not necessarily, or we do not necessarily have to determine from the graph, right? Seeing that we weren't told to draw the graph, or we weren't given the graph, right? So that is to say that you can calculate the quantities in a number of ways by simply using equations of motion or by using the graph itself, right? So looking at 1.3.2, they want us to calculate the total distance of the entire motion. So they want us to calculate the distance traveled from 0, right, back to here. So from here, they want us to calculate the entire distance, right, that the Yaris moved. Right, now you can do this in a number of ways. You can simply use the area under the graph, right, which we have discussed in the first video, right? But also now you can also use what I'm about to show you, right? If you look at our graph, right, our graph essentially has 3 sections, right? It has this section, called it section 1, call this section 2, call this section 3, right? If you section the graph into 3 parts, you get this triangle, the rectangle, and this triangle, right? Now in doing so, having to calculate the total distance, you can use each section of this graph to calculate the distance traveled in each section, and then just add the distances to get the total distance, right? One of the ways you can do that is by looking at each section individually, right? Like for instance, if you look at the first section, right, in this first section we are going to consider this straight line. In the section we are going to consider this straight line. In the third section we are going to consider that straight line, right? How do we do that? Now we are going to use what we call what is this? We are going to use what we call the average velocity, right? How are we going to use the average velocity when considering a straight line, right? Essentially, you look at 2 velocities, right? The initial velocity and the final velocity, right? So we are going to say S1 is equal to the average velocity in this section or in this straight line, average, right? Because essentially we are considering 2 points, this point and that point. The average will be this velocity plus this velocity divided by 2, right? So essentially we are saying in that straight line, the initial velocity plus the final velocity divided by 2, right? So this constitutes as the average velocity, right? Why? Because in this straight line, we are only considering this velocity, which is the initial velocity, and that velocity, which is the final velocity, right? So the initial plus the final divided by 2, this here is the average velocity for that straight line, times the time the object took to move from 0 to the final velocity in this section of the graph, right? So now you substituting initial velocity is 0, final velocity is 20 divided by 2 times t, right? T is 15 seconds, right? Now if you punch this in your calculators, you should get 150 meters, right? Now let's consider section 2 of the graph. So now we are going to consider this section of the graph by looking at that line, right? Remember the graph here is this one, right? This here is the section under the graph, right? So in section 2, the object is moving at a uniform velocity, right? But again, this is a straight line, so we are going to consider this point and this point. So doing the very same thing we did for the first section, we're now going to apply the very same concept for the second section, right? Now for the second section, right, the second section begins here and it ends there, So now this will be the initial velocity and this will be the final velocity. Right, so again we use initial plus final divided by 2. That's the average velocity in section 2 times the time. Right, now the time, remember, it is the time that the car took to move from this section or from this point to that point. Right, the time it took for the car to move from this point to that point. The time it took is essentially the difference between 30 and 15. Right, so here you can write t, or we can say contextually it is going to be t2 minus t1. Right, so that's t0, t1, t2, t3. Because we're looking for the time it took for the object to move from this point to that point, right, we are going to find the difference between 30 and 15. So t2 minus t1, right, is equal to, now the initial velocity and final velocity are the same. Why? Because the object is moving at uniform velocity. So the velocity of the car here is constant. So u is 20, also v is 20. So here you have 20 plus 20 divided by 2. That's the average velocity of section 2 times the time it took for the object to move, right, from here to there, which is 30 minus 15. So 30 minus 15, right? Now punching that in your calculators, right, you should get 300 meters, right? Now we calculate the distance moved in the third section. Right, this here represents the third section. Right, the third section begins here and it ends at that point. Right, so in the third section the car was decelerating, making this the initial velocity here, and that's the final velocity. Right, so using the very same formula, average velocity, there's only two velocities to consider, so it's u plus v divided by 2 times, right, this ends at t3. So to find the time that the object moves from this point to this point, we say t3 minus t2. Right, so this is t3 minus t2 is equal to, now what is the initial velocity, right, in section 3? That's the initial velocity, it's 20. The final velocity is 0. Remember, the car came to a final stop, right, at that point. So initial velocity is 20, final velocity is 0, divided by 2 times t3, which is 40, t2, which is 30. So t3 is 40 minus t2, which is 30. Right, even in the statement you are told that it takes 10 seconds for the car to decelerate. So 40 minus 30 is 10. Right, if you like here, by the way, you can simply just write 10. It is fine. Right, I used this for you guys to understand where the 10 comes from. Right, now if you punch this in your calculators, you should get 100 meters, right? And then to get the total distance traveled, right, it will then be s1 plus s2 plus s3, right? S1 was 150, so that's 150 plus S2, which is 300, plus S3, which is 100. Right, and here you should get 550 meters. Right, that is one of the ways in which you can calculate the total distance traveled by this car. Right, Now another way would be to calculate the area under the graph. Right, that's the most obvious one. Right, but I had to show you this one first because the other two we already discussed in the first video on motion, power, and energy. Right, so you can use this method or you can use area under the graph. Right, area under the graph, you have again 3 sections, so you look at the area under each section. Right, in this section the area is that of a triangle. In section 2 the area is the area of a rectangle. Section 3, triangle again. Right, so you simply calculate the area of each section and then you add it up. So essentially what I mean is, so S total will be equal to area of first section plus the area of the second section plus the area of the third section. Now what is the area of the first section? First section is a triangle. Right, the area of a triangle is half base times height, so it will be half the base here is the time. Right, so half base is the time t1 times height. The height is the final velocity. Right, so here you would have half the base is t1 times the height, which is the final velocity. Right, plus area 2 is that of a rectangle. Rectangle is length times breadth. The length here is the final velocity. The breadth is t2 minus t1. Right, so here you have v times, which is the length, and the breadth is t2 minus t1. Right, that's the area of the second section plus the area of the third section, which is a triangle. So this would be half base. Right, half base. The base is t3 minus t2. So this would be t3 minus t2 times the height, which is the final velocity. Right, the height, so the height is the v, final velocity. Right, and then now all you do is substitute. So you have half t1, which is 15 seconds, times v, which is 20, plus v is 20 times t2, which is 30 seconds, minus t1, which is 15, plus half times t3, which is 40, minus t2, which is 30, times v, which is 20 meters per second. Right, and then now all you do is add this up. Right, so you punch this exactly as it is in your calculators and you should get the same answer we got when using this approach. So you should get 550 here as well. 550 meters. Right, that's area under the graph. Another one, now for this case in particular, right, if you look at this shape, right, the shape looks like a trapezium, but in order for us to be able to take it as a trapezium, remember there's those conditions that need to be satisfied. Right, one condition being the two sides of this shape must be parallel. Right, now if you look at these two sides, they aren't parallel, but these two sides are parallel with each other. So you do have two sides that are parallel, and the two parallel sides must not be equal, right, in length. Now if you look at this one, is from here to there, and then this side is from here to there. So the sides are not parallel. I mean, the sides are parallel and not equal. So those two conditions pass. And then the other side, which is this one, you are going to take as the height. So we are able to take this as a trapezium because it has two parallel sides that aren't equal. And then the other side, which is this one, we are able to take as our height. Right, so we are going to take this side and this side as A and B. Remember, the area of a trapezium is equal to A plus B divided by 2 times H. So as long as there is a side you can take as A and a side you can take as B and one that you can take as the height, then you can take that shape as a trapezium. Right, so we can say that's A, that's B. Right, so A and B are the two sides that are parallel and not equal. Right, and then H would be the other side, which is this one. Right, so the area here, because if you look at this one, right, it considers the entire graph. So here you would then say, this is another approach you can use, total distance, right, using the area of a trapezium. Right, area of a trapezium being this one. So you're going to take this as A. So A is 30 minus 15. Right, so from here to there is 30 minus 15. From here to there is essentially T3. Right, so we can say here, area of a trapezium, you have T2 minus, not T2, you have T3 minus T2, right, which is essentially A, right, from here to there. So this is T2 minus T1, my mistake. So this is T2 minus T1. So that's T2 minus T1, right, plus, so this side we said we're going to treat as A. So from here to there is T2 minus T1 plus from here to there. So that's A, and from here to there is B. Right, so from here to there is T3. So this plus T3 divided by 2. So essentially meaning that's A plus B divided by 2 times the side we are going to take, as our height, which is this one. From here to there is V, the final velocity. So here, our H we are going to take as V. Right? This is equal to, so now you just substitute. Right? T2 is 30, T1 is 15, plus T3, which is 40, divided by 2 times V, which is 20 meters per second, is equal to, now if you punch this in your calculators, you should get the same thing that you got when using this approach or when using this approach, which is 550. Right, so you should get 550 here again. Right, so those are the three approaches you can use to calculate, for this problem, to calculate the distance moved by the car. So they said the total distance moved by the car, or the total distance of the entire motion. Right. Then now let's look at 1.3.3, calculate the average velocity in 40 seconds. So now they want us to calculate the average velocity, right, considering the entire span of the car's motion. Right, so from here to there, right, they want us to calculate the average velocity. So this is 1.3.3. And this is how you calculate the average velocity. All right. Consider this triangle. Right. Here you have average velocity, there you have total distance, and here you have total time. Right? So for cases where you have different sections of the motion's object, you simply use this triangle, right, to calculate your average velocity. Right? You've just calculated the total distance, you have the total time, so you are able to calculate the average velocity. Right? Now you must be careful though, because they could ask you to calculate, for instance, the average velocity for the first 15 seconds. They also could say calculate the average velocity where the object or where the car was moving at a uniform velocity. Or they could say calculate the average velocity where the car was decelerating. Now remember, we've already discussed that when looking at each section, so for instance, if they say calculate the average velocity for the first 15 seconds, so it means you're looking at this section, right? In this section, you have this velocity and that velocity to consider. So the average velocity would simply be this velocity plus this velocity divided by 2. The same way we did here. Remember I said that this represents the average velocity for this section. Right? And then if they say, for instance, calculate the average velocity where the car is moving at uniform velocity, this is where the car is moving at uniform velocity. So if you were to calculate the average velocity here, you would consider this velocity and that velocity and divide it by 2. You are dividing it by 2 because you are only considering 2 points. First point, last point of this section. But now when you consider the entire motion of the car, right, you can't simply take the first velocity and the last velocity. Your answer won't be accurate. So for accuracy purposes, right, in considering the entire span of the car's motion, right, you make use of this triangle. Right, you make use of this triangle because we are considering the entire span of the car. Right, so using this triangle, right, using this triangle, so what it is that we are looking for V average. So you block that, we are looking for V average. Right, we're looking for V average. So blocking V average, you are left with S divided by T. So it means that V average is equal to total distance divided by total time. Right, that is how you use this triangle. Right, if you were given the average velocity of the entire motion, of the entire span of the car's motion, and you were looking for the total distance, right, you can simply do the same. Right, if you are looking for this thing, if you are looking for this instead, right, it means you would have ST is equal to V average times total time. So this would be average velocity times T, right, which corresponds, if you think about it, with the first approach we used in calculating the distance. Right, average velocity times time is the same as that. Right, but this method, of course, you would use if this is given. So if you are given the average velocity of the entire span of the car's motion, right? So that is how you use this triangle. Right now we're looking for the average velocity. We have the total distance and we have the total time. Total distance we just calculated and got 550 meters divided by the total time, which was 40 seconds. Now if you punch this in your calculators, you should get 13 0.75 meters per second. Right, meters per second can also be expressed as meters per second. So it's up to you. You can either use this or that. It's the same thing. Right? So that's 1.3.3. Now let's look at 1.4. Make a sketch of a velocity time graph for the total duration of motion of the Toyota Yaris. Right, essentially we've already done that. Right. So when doing 1.4, this is what you do. Right, so you have, this is 1.4, and this is how you would draw the graph. But now, because you've been told to draw the graph, this one you would have to draw neatly. Right, unlike when doing 1.3, right, because essentially we weren't asked to draw the graph, right? But for context, you would draw the graph, say, on your question paper, roughly, right? But because now they've asked us to draw the graph, right, on 1.4, you have to draw this one neatly, right? Right, and that is how we attempt problems essentially on motion, right, by either using equations of motion or by using the graph itself. Right, I trust this was of help to you. Stay tuned for more videos. Please like and subscribe to the channel so that you don't miss any other content on engineering science entry. Nature God signing out.